So with this particular question and how it's phrased, it becomes a little bit tricky because people can't quite grasp kind of where you need to solve for. Okay, so if we're talking about the reaction happens spontaneously, we're looking at a delta G that must be negative. If it was unspontaneous or non-spontaneous, that delta G would be positive. So we're looking at the exact point at which we transition between positive to negative. What is the exact point on which we transition? Where do you transition between positive and negative numbers? 0. So what we need to go through and solve for is the delta G at 0. You can now just go through and set up your system where you're now plugging and chugging. 0 equals 178.3 kilojoules per mole minus your temperature, we don't know the temperature, times your delta S, 160.2 joules per mole, okay, times our Kelvin. Speak up. Somebody mumbled something.
Shouldn't the delta S be in kilojoules?
Okay, if we're going to deal with our proper unit conversions, does our delta S need to be in kilojoules? Yeah. So we will end up having to convert that across, depending on how you want to manipulate that. We need to make that kilojoules, and now it's just a question of solving for temperature. Subtract things across, all that stuff. Do our algebra, and what are we going to get? A couple people told me 1,113 kelvins. Okay, thereabout. Okay, so what does that mean? To make our cement, we need a ton of heat. Okay? This reaction is not favorable at all, so to force it to actually occur, we have to drive the temperature through the roof. Okay, is that going to take a lot of energy? Yeah, that's going to take a whole ton of energy. Okay, and if we go through and look at this, okay, we produce or need so much energy in the production of concrete, right, that it produces a lot of CO2. It's one of our dirtiest contributors for greenhouse gases. So there's a lot of active research, both to kind of greenify it, if you will, okay, to make it produce less CO2, okay, but also to make it use less energy. Okay. However you want to look at it, those being kind of the optimists might go through and say we're trying to make things better for our planet. Other people might just say we're just trying to drop the costs of it so it doesn't cost as much. Okay, so we can make larger profits off of these. Either way you look at it, the production of concrete is very, very, very expensive. Okay. Do we have evidence of that? Yeah, what's our evidence that it's expensive? How did you get to school today? On a road. What was the road made out of? You might be like, it's concrete on the highways. On the highways it is, okay, but not on our main city streets. Our main city streets are made of asphalt because it's significantly cheaper to produce that material. Okay? And even on our highways, you'll see some highways are made of asphalt, but even then it becomes trickier. Okay, why does it become trickier? What typically moves on our highways? Very large trucks. Very large trucks put a lot of weight down on the road, and it would distort and warp the asphalt with the amount of frequency that they were driving over it. So our concrete is a better material in that respect. All right? It's also so expensive we don't use it everywhere else. Which gets us to the next fun slide. All right, we've got F reaction processes. What you want to go through and do is look at the delta H and the delta S for each of these particular reactions. All right, you'll note there is no numbers to quantify this. What you're doing it based off of is your understanding of what's happening. So you want to place them in the corresponding boxes on whether they are always spontaneous or spontaneous at low temperatures, spontaneous at high, or not spontaneous. Go through and evaluate, talk at your table to explain why for each of them, and then we will discuss. So what's happening in A? Okay? So if we're going to say spontaneous at high temperature, we're saying a positive delta H and a positive delta S. Okay? Where I want to start first and foremost is that while that could possibly be correct, you're making a really big leap. So instead of going through and looking at each of these conditions and saying, well, A, I think it's a positive delta, well, what's a positive delta H? If you can't answer that question, telling me it's spontaneous at high temperatures is problematic. Because the only reason you can get to spontaneous at higher temperatures is you know what a positive delta H means. Otherwise, all you've done is guess. Okay? And in this particular scenario, that's a 25% chance of you getting right. Are you happy with 25% odds on your exam? No, then do better. Slow down and look at each of the pieces of information that would take you to that potential conclusion. So if we're going to say it's spontaneous at high temperature, let's look at the delta H first. What does a positive delta H mean? Endothermic, which means we had to add heat into the system. When we look at combustion, okay, combustion, car engines, a log of wood in the fire. Okay, why do we burn wood? Why are we combusting wood in the fire? To generate heat. It's releasing heat, which means that would be exothermic, not endothermic. Okay? So that would suggest we aren't looking at a positive delta H, we'd be looking at a negative delta H. Okay? What about the delta S? Okay? We're saying a positive. Okay, so that's good. We hit that quadrant, but why should it be positive? What about looking at the equation allows us to tell that it's positive? One statement I think I heard was, well, it's exo. Exo is all about enthalpy, not entropy. So when we're looking at entropy, the first baseline starting point, to give you an idea, okay, is to think about the motion of our particles. This is why we could start looking at phases. Okay, after phases, where could we look? The number of particles. Okay, after the number of particles, what could we look at?
Temperature.
We could look at temperature. After temperature, what could we look at? And this might be where you go like, I don't know. We didn't talk about that. We did vaguely talk about it, but in general loose terms isn't kind of a random thought. Okay. Actually, I'm not sure we talked about it in this class. Okay. That's starting to drill into deeper and deeper understandings for our entropy, and we don't need that level of thought, at least at this point. Okay. So for this particular case, we could start with phases. Do we see the phase change? No. So the phase isn't going to help us out. So the next thing we could look at, the number of particles. How many particles do I have on the reactant side? How many particles do I have on the product side? What happened? Entropy went up. Right? And if the entropy went up, that would be a positive delta H, which would mean always spontaneous. Yes, sir?
Times where it's like equal, 6 and 6.
There could be. Okay? There could be times where we don't see a difference in the number of particles. Okay? What would you do then? We just talked through it. Where do we first start with our entropy? Phases. Then we go to numbers, and then we go to our temperature. Okay? And if all those are tied, you're right. Now you're like, well, how do I figure that out? And that does become a much more challenging question. And I think one that is we're going to sidestep and say is beyond the scope of what we're looking at. Okay? I think somebody up here might have started to mention it. You can look at the complexity of the individual molecule. The more,
Right about.
yeah, that's when you're starting to look at how that structure and its possible individual motion can contribute to the overall entropy. Oh, we did. Cool. All right. Does that make sense?
I understand the mechanisms of solving it using this table, but saying a combustion reaction like that is always spontaneous, just it isn't clicking for me. Like, why is it always spontaneous? Because when you say it like that, it kind of implies that if you expose it to air, it's going to immediately react.
Okay, which it does.
Yeah.
It does. When I expose wood to air, it absolutely does immediately react. Okay, and that's the tricky part. Everybody's, well, but I don't see any changes. Just because you don't see a change doesn't mean it's not reacting. Okay? How long, just exposed to air, does it take to do that chemical reaction? A longer time. That could take hundreds of years. Okay? So the tricky part is that when we talk about spontaneous, what you're bringing in is English language interpretation. English language with spontaneous means instantaneous. It's a speed. There is no speed. Spontaneous in this case is just referring to the fact that it happens. Okay? And it will continue to happen. Given enough time, our reaction will proceed.
Could you say that about anything? Like
Nope.
Stuff rusts over time?
Nope. Let's look at photosynthesis. Am I going to be able to take CO2, react it with water to produce glucose spontaneously? That will never happen. Why will that never happen spontaneously? Well, it's endothermic, which means our delta S is, delta H. It's positive. Okay? What happens to the delta S? It's negative. I can't mix carbon dioxide with water and just have it form glucose. It's never going to happen on its own. Okay? And that's looking at the balance of entropy and enthalpy and how those things interact. One of the things, again, that we start to bring in is kinetics. Kinetics is not part of the discussion. All we care about is the raw energy difference between reactants and products. The only way we go up is that we have to contribute something to the system. That's not spontaneous.
I was going to just help out with like the...
Go for it.
Because it stated in the previous slide that spontaneous means that the reaction can happen without an input of energy in this sense.
Yep. And to me, that without the input of energy becomes a little bit challenging for people, I think, to grab a hold of and use. Because when we think about without the input of energy, if I just put that log down, I don't see it immediately change. But if I clear the activation barrier, what happens?
You light it on fire.
I light it on fire and now it runs. And so we start to bring in this activation barrier concept. Okay? The problem with that is activation barrier is kinetics. That's all about the speed of the chemical reaction. I don't care about how fast the reaction happens. I just care if it will happen. Okay? Thermodynamics just says, I'm going downhill. That's it. And the things that will contribute to that downhill energy are my enthalpy and my entropy. I don't care about the speed at which it happens. Okay? I circled that one. That was what B was down here. Salt dissolving in water, we already identified in C. Okay. What happens to the delta H? Okay. I'm breaking a bond. How do I break that bond?
Energy?
With energy. I have to add energy in. If I add energy in, that means heat is a reactant, and I'm looking at endothermic, which means delta H is positive. What happens to my entropy? I'm going from a solid to aqueous. We're increasing our possible motion states, which again suggests a positive delta S, which then means we sit in that lower left-hand corner for our box, spontaneous at high temperatures. Does that make sense? All right. Should we continue to look at the other ones? Oh, we heard a yes. Okay. Boiling water. Okay, what do I have to do to boil water? Okay. Am I breaking bonds? No, am I breaking something else? Yeah, what am I breaking? Forces. I'm breaking the intermolecular forces holding individual water molecules next to each other. I had to add energy to break those interactions. Okay, which means where's my heat term? It's on my reactant side. It's not really an enthalpy, but we can look at how the heat is acting in this particular system. Okay, because we aren't breaking a bond. Okay, we could also go through and look at the entropy. What's our entropy? Positive. Where does that put us? Spontaneous at high temperatures. If I take water and I add heat to it, okay, when does it spontaneously transition from a liquid to a gas? Does it do that at 1 degree Celsius? No. Does it do it at 101 degrees Celsius? Boiling point of water is 100 degrees. Yeah, it's going to spontaneously make that transition. How about freezing water? Okay, now you're flipping the system. Heat is lost in this process. Heat is given off to our surroundings. That's why we can transition from the liquid to the solid, which is putting us in this negative delta H-ish category. We're forming stronger interactions, not chemical bonds, but intermolecular forces. Okay. What happened to my entropy? It decreased, which means spontaneous at low temperatures. Can I form solid when I'm at 100 degrees Celsius? No. But if I drop the temperature to negative 10 degrees Celsius, yeah, I'm going to spontaneously see the formation of solid. Kind of make sense? Last one. That one's a challenging one. Okay, again, we push on this no heat kind of concept. There isn't really a large temperature change when you're dealing with that one. Technically, you are breaking intermolecular forces. You're breaking the intermolecular forces between water molecules, which requires energy. Okay. That energy, when we're trying to mix them, is coming from where? It's the ambient temperature that we're at. Okay. So we're looking again at adding heat in, a positive. Okay. What happens with our entropy? That's a weird one, right? They're both liquids. Where do we have more entropy? When they're separate from each other or when they're mixed? When they're mixed, they now can occupy more states. So we're looking at a positive delta H and a positive delta S. What does that suggest? Only works when we're at high temperature. What's that high temperature being used to do? Break the intermolecular forces and force that mixing process to happen. Kind of neat. And what I would argue is kind of neat behind this is how many calculations do we run? Absolutely none. But we now have some building blocks that we could start to predict how successful an individual chemical reaction would be.
Hypothetically, if like you could mix oil and water in like a low temp, it would still be spontaneous.
How are you mixing it though? So, and that's...
So I guess it's just increasing, it's not positive. It would be like if it was like negative temperature, but it went more, it increased but still negative.
So you can force those things to mix, but you're now changing the system. If you're forcing it to happen, is that spontaneous?
No.
So the spontaneous is it just there, doing its thing.
Okay.
It's kind of neat. Okay. So, phase changes referencing our entropy of our system. So, liquid or solid up to gas, we increase our entropy. Okay. Freezing systems, our entropy of our system decreases, right? Because we're reducing our potential motion. Okay. They're exothermic reactions. Okay, because we had to remove the energy of those individual particles. Okay? This is why, what do we notice outside our refrigerator? Anybody tested? Walked around the outside of your refrigerator? It's really hot. Why? It's taking all the heat that was stored in your individual compounds inside the fridge, and it's removing that heat. That's why it keeps the inside cold. Your outside is necessarily going to get hot. Okay? You can sort of flip it and look at boiling. Your entropy of your system is going to increase. It is going to be an endothermic reaction because you had to put energy in to cause it to change that phase. Okay? And since nobody loves just general thought games, let's go ahead and do a calculation. Hooray, calculations. Calculate the entropy change for this reaction. A little bit of review. I guess to put us all on equal ground, how do we do it? Our products minus reactants, we need a little bit more than that. The N value
Some of the products.
and the sums. I'm also trusting you memorize that formula correct. So in theory, we should have our formula roughly set up. Note, I'm using the parentheses to help kind of emphasize the fact of how my minus sign is going to distribute. In this case, it's not a big deal because I only have one product. And because I only have one product, the minus sign isn't distributing very far. It's really only just going to one thing. I didn't put any N values in there. Why not? They were all officially 1. But if they're all officially 1, this is 38.1 joules per mole of what? Per mole of calcium oxide. That's where our 38.1 came from. Am I allowed to add that to 213.8 joules per mole of CO2? Those units are not the same. I'm not allowed to do it. Why am I allowed to add it? Did I include the 1? Technically, I did. 1 mole of calcium oxide. The mole units can now cancel out. I would not have a space in here, but I also have my mole of CO2. So the moles of CO2 can cancel. Now I can run that calculation. That's why that N must be there. Even though numerically it's not doing anything, unit-wise it does a lot for us. Okay? We run the calculation. So somebody had a number. Did you get a number? 160.2 joules per Kelvin. And I would argue in this particular unit that I wouldn't leave it actually in my written work as 160.2 joules per Kelvin. What do you think I might want to add to this? Yeah, there it was. But I'm looking at the sign on this. It's a positive value, it's going up. Right? A lot of what we're doing is looking at these positives and negatives, and if I accidentally drop that sign off, it could change my interpretation significantly. So I personally would want to add extra emphasis to that sign so that I know what's happening within it. Does that make sense? We good? Okay. For this next slide, I should probably stop recording. I don't know why this slide is here. I've stared at it for a little bit. I can't figure it out. Okay? So if we're looking at cement setting to turn into solid cement, it's an exothermic reaction. You add water. The water reacts and converts to make calcium hydroxide and our calcium silicate hydrate. Yay? Sorry, Dr. Sheblin. That's all I got.
Is adding water adding energy? So this is spontaneous?
So deciding whether it was spontaneous or not, what would we have to evaluate? Delta H and our delta S. So you could go through, we're already told it's an exothermic reaction. If it's exothermic, what does that mean? It's negative. That suggests spontaneous. We could look then to the next thing, which would be our entropy. What's happening with our entropy? It's going down. Is that spontaneous?
At low temps, which
Right?
can be spent.
So this is now dependent on the temperature for our concrete to set.
Positive H, negative S, non-spontaneous?
It's a negative H, exothermic.
Oh,
Yeah. So it is temperature dependent. Maybe that's the question that was supposed to be asked. So good job. Okay. We can also look to biology. Okay. A protein will fold into its three-dimensional shape by forming hydrogen bonds and other intermolecular forces with large molecules. So if we look at most protein sequences, it's just a chain of amino acids, if you haven't learned that, okay, in your biology class. So it's just a really long chain. Okay? That chain will fold in certain ways to minimize its interaction with other things or maximize its interaction with other things. Okay? That process is sometimes guided, sometimes not, and it folds. So what we're seeing here from the unfolded to the folded state is in the folded state we have these helix, or these helices. Those are known as alpha helices. Okay? Depending on the system, those may form on their own, they may not. Okay? Which sets us up with the question, is the folded protein more or less energetically stable? Does the folded protein have higher or lower entropy? Again, blue box, this is words from your mouth at your table. So what do we think? Is the folded protein more or less energetically stable? It's going to be more stable. Okay? What we've done is locked it in that space and created strong interactions. Okay? So we've rearranged it to make it a more stable structure. To break it apart, we'd have to put energy in to break those strong interactions. Okay? Does the folded protein have higher or lower entropy? Lower entropy, there's less possible motion. That's why we have these helices. Okay? The unfolded protein doesn't have those helices. They can free move wherever. Folded, we have to maintain that helical shape. Right? What does that suggest about the spontaneity? It's spontaneous at low temp. What's going to happen when it gets hot? It would be a non-spontaneous reaction. If it gets hot, we would never go from the unfolded state to the folded state. Yes?
Explain how you brought temperature into it.
Sorry, say again?
Can you explain how you brought temperature into that?
How we brought temperature in. So what I was referencing there, previous slide, we went through and said our delta H and our delta S. Okay. Our delta H, come back here, where'd it go? There it is. Our delta H, we said was more stable, okay, and our entropy went down. We're spontaneous at low temperature. That's how we brought temperature in, okay? And ultimately, where's this table coming from?
Formula?
What formula? Say again? Yeah, that's our Gibbs free energy all the way back there. Okay, kind of, sort of? Cool, cool. Sorry. Okay, so would this process happen at lower, oh man, that's what happens when you get excited about things. Okay, we've got our energy diagram depicting what's going on. We've got our delta H and our delta S already identified. Okay, within this, lower high temperatures, that's spontaneous at low temperatures. Okay. As you identify your delta H's and delta S's, the immediate response should be immediately thinking about what does that mean to delta G? What does that mean to delta G? Because that is almost always going to be a follow-up question. Ta-da! Okay? What do you think happens? Oh, man. What do you think happens when we increase the temperature? What's that?
The protein folds.
Does the protein fold? What did we say? It was spontaneous at low temperatures. So if we increase the temperature, the reverse reaction is spontaneous, and it should actually unfold. Ooh, bringing in the idea of reverse concepts. That's dangerous. Okay, our Alex homework due this Sunday. I believe those are my office hours. People have been trying to schedule retakes, and I've been asking for emails just as confirmation. As long as you're hitting those times, it shouldn't matter. So you can just freely show up if you wanted to. I will say, unfortunately, this Friday, I'm also going to miss the tutoring center. In my office hours, I will be there from 10 to 12, though. So, or 10 to 12:45, I think. So if you wanted to try and do this Friday for a retake, you could do that too. Hi. We usually think of our reactions going in one direction. Okay, so thermodynamics tells us whether the reaction will happen, regardless of time. Kinetics will tell us how fast the reaction happens. We use spontaneous to reference the thermodynamics aspect, and we just talk about how fast a reaction goes when we talk about kinetics. So again, spontaneous just means it will happen, and that's it. Okay? But this does introduce, particularly based off of that last conversation we had about protein folding, an interesting dilemma. Okay? The reaction can go both ways. Okay? Small organic chemistry pet peeve that I'm going to complain about. This arrow is a bad arrow because it implies something else. What we're talking about is a reaction progressing forwards and progressing backwards. Okay? This should be a relatively new concept. We have the ability for both of these things to happen. And if we change the directionality of our reaction, we're going to get the opposite delta H, delta S, and delta Gs. Okay? All of those systems are now just going to swap. Okay? Are the numbers going to change? No, because it's just running the reverse. You just get all of those becoming the opposite sign. Okay? The rate of your forwards and the rate of your reverse reactions are not necessarily equal, which is a good thing. Okay? If we're talking about the protein folding process, we're made up of proteins that do different chemical reactions for us in our body. If the rate of the reverse unfolding process was equal to the rate of the fold process, what happens to our active proteins? They disappear. So we would need twice as much protein structure to actually maintain the activity of our individual cells. Okay? That is going to get a bit absurd when we consider size. Okay? Which then sets us up with a fun little demonstration, okay, that you guys are going to run at your tables. Okay? Probably easiest to work with the person immediately next to you. So I would recommend jumping somewhere. Okay? Find a partner, decide who's partner A, who's partner B. Okay? For the front tables, that's this front table. Well, it's probably just going to be you, front table. Okay? Partner A starts with $100. Partner B starts with $0. Okay? For our middle tables, partner A starts with 50. Partner B starts with 50. For the back tables, partner A starts with 50. Partner B starts with 150. Right? And what you're going to go through and do is exchange money. Right? On each exchange, A gives B 40% of what they have. Right? So you're going to have to run some calculations. And B gives A 30% of what they have. Right? Don't do the trade and then say, well, now let me calculate. You calculate how much you're going to trade, then you trade, look at your new total, then what do?
Do it again.
You do it again. You do it again. You do it again. And we want to repeat this process for 10 exchanges. Right? Get an idea of the rules? Okay. This requires you talking to each other to run these calculations. Okay? To give you an idea of where we're going with this, okay, we can look at a table. Okay, your number of exchanges Partner A, partner B. What you have at the end of each of those cycles. Do the exchange, do the exchange, do the exchange. What we're going to look at is what do you end up with at 10. After 10 exchanges, we're going to look at each of those groups. Are we ready to give this a shot? Don't all be excited at once. Yes, we are ready to give this a shot. So we'll see how it happens. So group 1, after 10 exchanges, how much did partner A have?
4286.
So what do we notice? What do you guys notice between group 1 and group 2?
I've seen this recent formula.
Those are really close. They started with a completely different balance of money, and yet at the end of this result, they get the exact same result. That's kind of crazy. That's a little weird. Okay. What about group 3? Oh, they got something way different, right? Why would they get something way different? I'm going to come back to you in a second. Why would they get something way different?
They started with twice as much money.
They started with more money. Because they started with more money, that's going to change the dynamics at the end. You said it's not that different. Why is it not that different?
It's just the same numbers but backwards.
Ah. If we look, since we started with twice the amount, what did we end with? Twice the amount. The ratios still came out to be the same. What we're looking at here is the concept of equilibrium. If you wanted to move back, you can. Okay, you could stay there too. I'm not making you move. Okay, this is what we're thinking about when we look at equilibrium. And as you ran through those calculations, I think a couple calculations in, you probably started to notice that the transfer back and forth started to become about the exact same. Okay, we could still transfer money back and forth. What's going to happen to the numbers? They're going to maintain the same. Okay, so what we're looking at in those initial stages is the rate of the reaction. Okay, but what we're now bringing in after 10 exchanges, so we ignore time and we just look at the end result. We look at the place where the transfer starts effectively canceling out and we don't see a net change. This is the concept of equilibrium. Okay, that's what this demonstration is trying to get at. Okay, this is dynamic equilibrium. So when we look at a reaction, they occur in both directions. Okay, here with fancier technology, you can see better arrows. Okay, equilibrium exists when the rate of the forward equals the rate of the backward reaction. That's when you've achieved equilibrium. So when you run through those calculations, when the amount of money being transferred back and forth was the same, you've achieved equilibrium. How long it took you to get there is dependent on other things. That would be the kinetics of our reactions. Okay? The next important thing to kind of consider is what happens when we get to that point. Okay? If you look at your trials, okay, did you start transferring the same money before trial 10? Yeah. Okay. I think what I saw, you started transferring roughly the same money with each other about trial 4 or 5. Okay. Did you continue to transfer money? Yes. Why? Why did you not just stop at trial 4 or 5? Because you were told you had to run 10 trials. Okay. Reactions aren't told to stop. When do they stop? They don't. They will continue on forever doing this transfer back and forth. So the big word that kind of comes out of this that we have to be careful with is dynamic. Our reaction is constantly going backwards and forwards. We eventually reach a point where the transfer doesn't change the overall balance of the reactants and products, which then gives us an opportunity to evaluate the balance of reactants and products, okay, for an individual reaction. Right? So if we look at the plot that we're seeing here on the right, we're looking at concentration. That concentration simultaneously represents our NO2 and our N2O4 from this chemical reaction. Okay? What happens to the NO2? Well, the NO2 as a reactant concentration is going to go down. What happens to the concentration of N2O4? It's going to go up. Okay? And we've seen this before, right? Didn't we see this plot before? We saw this plot when we talked about kinetics. We looked at concentration versus time. Except when we looked at it in kinetics, what did we do? We truncated it. We really only looked at that initial part. And we stopped paying attention to that last part. Why? What's happening to the rate of the reaction when it flatlines like that? It's not changing. It's constant. And if that's constant, we don't care about it anymore because rate is how fast that it happens. Okay? So our kinetics chapter cared about that initial part, and our thermodynamics cares about this part. Kind of, sort of? Okay. This shows up later in the slides, so I'm not going to go through it in detail, but I am going to tell you that you should go through and look at this. The rate forward equals the rate backwards. What would the rate forward be for the reaction shown below? Assume this is a mechanistic step. What would our rate forward equal? That's right, the rate constant. Okay, the rate constant times what? Concentration of our reactants. Okay, we're going to ignore order just for simplicity. And we're saying this is going to equal what? The rate backwards. What's the rate for the backwards reaction? K, awesome. Is it the same K? No, it's a different K because that K is looking at a different chemical reaction. That's looking at converting N2O4 into NO2. We're looking effectively at a synthesis versus a decomposition. Those are different rate constants. Times the concentration of the reactants for the backward reaction. What's the reactant for the backward reaction? That would be our products when we look at the equation as it's written, our N2O4. Are those Ks the same? No. So it might be nice to add a little bit of information so that we know they're different. Okay? We could color code them, but what if you don't have colors? Right? We could call them K1, K2, or we could say the red K was the K for the forward reaction, F. And orange K was backwards or reverse reaction, I use R. What becomes interesting or fun about this? What are the Ks? They're constants, and the concentrations are concentrations. What do mathematicians like to do? Simplify by grouping like terms. I said I wasn't going to derive it. I just derived it. What is a constant divided by a constant? Another constant. So we could go through and we could define the rate constant of the forward divided by the rate constant of the reverse to be equal to some new constant. When does this constant come into existence? Comes into existence when the rate forward equals the rate backwards. What does it mean when I have the rate forward and the rate equal to the rate backwards? Big word at the top. I'm at equilibrium. So I could define a constant when I'm at equilibrium. Okay, that's interesting. Okay, what this is going to create is this equilibrium ratio. Okay. The constant that we produce that comes out of this for an individual chemical reaction, the balance of products to reactants at equilibrium will always be the same thing. That's what we saw. Table 3, we had started with $200 and we ended with the exact same ratio as tables 1 and 2. That was constant for that reaction. What was that reaction? How much money were you allowed to transfer back and forth? That was the rates for those particular reactions. Okay? Since we have this new constant, we want to define it. We'll call it the equilibrium constant. And because it's a constant, we don't want to write out equilibrium constant all the time. We want to come up with a new symbol to represent that. What symbol do we choose? It is on the slide. We choose K. Capital K. Not lowercase k, because lowercase k was our rate constant. Capital K is our equilibrium constant. Numerically, they are very different. Okay? They also describe very different actions. Our rate constant k is all about speed. Our equilibrium k is all about once it's balanced out. Very, very different meanings, so we have to be very careful with them. You'll typically see some kind of subscript written next to the k. That is to imply some extra information. So you could see it written as KEQ. EQ for equilibrium. You could also see it written as KC. What does the C stand for? Not constant. Concentration. Because when we derived it, what did we have? We had the products over the reactants in brackets. And what do those brackets mean? Concentration. Right? So you could see it written as KC. You can also see it just written as a blank, normal capital K. Okay? You could also see it written as KA or KB. Okay? There's a bunch of extra terms that can get added to it. The A and the B you'll see later this semester. Don't stress about them right now. Okay? Typically, it's written in terms of concentration. Okay? Should it be written in terms of concentration for gases? I mean, you could theoretically do that for a gas, but more than likely, what's the better measure for gases? How do you measure gases? Pressure. So we could also see K, P for pressure. That gives us some context of what units we're using when we solve and build this system out. Okay? So, some practice. Write the equilibrium expression for each of these reactions. Talk to the people around you, see what you come up with. It's not a race, but it is. Your equilibrium expressions are up on the board. There's some things that we want to discuss. The exponents are going to directly derive into our expression. Right? Those exponents would be our coefficients. How else could we see this written out? It's the concentration of our products, which is NH3 times NH3, also known as NH3 squared. Okay? So this is nice. Those exponents are not orders. So don't treat them as orders. You can pull those directly from your chemical expression. Hooray! Don't have to do a bunch of calculations. Okay? Now let's take a look at the black and the orange expressions. Is there anything weird about those expressions? Yes. What did the brackets mean? Concentration. It's how much is in a given volume. Say again? It is aqueous, yeah. And if it's aqueous, would I be able to present how much was in a given volume? Yeah. Okay. How many of the bromide ions were floating around in a solution of water? Yeah, that makes perfect sense for a concentration. So I like the aqueous, but shift your focus. Not at the aqueous, how about the liquid? How much water is floating around inside water? And if that sounds like a weird statement, that's because it is. If you're given a solution of water, guess what its concentration is? Constant. Its concentration will not change. And if it's constant, what can we do? We can drop that term. Okay? So we care about solutions, aqueous. What's happening in the orange one? We care about solutions. Do we have any solutions? No. So does that mean everything gets canceled out and I have no equilibrium expression? No. Okay. What else did we say the equilibrium expression could represent? Not just solutions, but also pressure, as in gases. So gases occupy a volume. I can look at a concentration, the amount of particles in the volume of the container that it's looking at. So absolutely CO2 is okay. But how about those solids? Is the concentration going to change? If I have a solid, I have the solid. Its concentration is, again, constant. And if it's constant, what can I do? I can delete those systems or those materials from my equilibrium expression. Okay? That's pretty hugely important when we're considering our equilibrium expressions. Okay? And with that, let's see, do I have a neat summary slide? I don't have a neat summary slide. We'll just call it right there.